Module 2, Lecture B, Features and Targets. By the end of this lecture, you will be able to define features and targets in the context of supervised learning, identify features and targets in simple problem descriptions and tables, and compare alternative feature choices for a basic prediction task. Features and targets. Understanding features. In supervised learning, features are the pieces of information a model uses to make predictions. Each row in a dataset represents one instance, and the features are the columns that describe it. For example, in a housing dataset, features can include house size, number of bedrooms, age, and distance from the city center. By analyzing these features across many instances, the learning algorithm discovers patterns. Without features, the model would have no data to learn from and could not make predictions. In machine learning, features can be numerical values like income or temperature, categorical values like country or product type, or binary indicators such as whether a patient smokes. Raw data often needs to be transformed into more useful features, for example, by turning a timestamp into the hour of the day or a flag for whether it is a weekend. These transformations do not change the underlying information, but they present it in a way that makes patterns easier for the learning algorithm to detect. When choosing features for a supervised learning model, they must be both relevant to the outcome and actually available at prediction time. For example, to predict whether a student will pass a course before the term ends, you can use attendance and quiz performance, but not the final exam score. Likewise, for predicting loan repayment, you can use information like credit history and income, but not future events such as whether the person eventually defaults. Carefully selecting only observable and pertinent features is essential for building effective predictive models. Understanding targets. In supervised learning, the target is the specific outcome we want the model to predict, such as the price of a house. During training, we provide examples where both the input features and the correct target values are known, so the model can learn how they are related. For instance, it might see houses with given sizes and locations along with their actual selling prices and adjust its predictions to better match those prices. Without a clearly defined target, the model would have nothing to guide its learning, and the problem would not be well defined. In supervised learning, the type of target we want to predict shapes how we build and judge our models. For regression, the target is a continuous value, such as a temperature or a revenue amount, while for classification, it is a category, like a spam label or a species name. Some problems use more complex targets, such as sequences or other structured outputs, but the core goal is always to map input features to the desired target. Understanding what kind of target we have is essential for choosing suitable algorithms and evaluation metrics, even if we do not know every technical detail. In supervised learning, the target values come from real-world data, so they can be noisy, ambiguous, or biased. They may be based on measurements, human judgments, or existing records, each of which can introduce errors or inconsistencies. For example, medical diagnoses can vary between doctors, and credit scores can be influenced by changing economic conditions. Because the way we define and collect targets shapes what the model learns, we must design this process carefully to support both accurate and fair systems. Real-world examples. In supervised learning, a model predicts a target value, such as a house's sale price, using input features like size, number of rooms, age, and location. The model is trained on past examples where these features are paired with known prices, allowing it to learn patterns that connect certain feature combinations to specific price levels. Once trained, it can take a new house with known features but an unknown price and estimate what that price should be. This illustrates how features and targets work together in supervised learning to make predictions. In healthcare, A hospital can use a predictive model to decide whether a patient is at high risk of developing a certain condition within a year, with the target being a simple yes or no outcome. The model is trained on past patient data that includes factors such as age, sex, blood pressure, cholesterol, smoking status, family history, and lab results, along with whether the condition actually developed. By learning patterns from these labeled examples, the system can estimate the likelihood that a new patient will develop the condition. This prediction then helps guide preventive care or the need for further tests. In email spam filtering, supervised learning is used to decide whether a message is spam or not. The model is trained on emails that have already been labeled based on user actions or judgments. It looks at features such as certain words, the length of the subject line, and sender information, and learns patterns that distinguish spam from legitimate messages. When a new email arrives, the model uses what it has learned to predict its category and route it to the inbox or the spam folder. Choosing prediction targets. Defining prediction questions. When building a predictive model, the first step is to clearly define the prediction question, which means deciding what entity you are predicting for, what outcome you care about, and when the prediction is made. For example, in healthcare, you might predict whether a patient will be readmitted within 30 days of discharge, where the entity is the patient admission, the outcome is readmission, and the prediction happens at admission time. Once this question is set, you create a target variable that records whether readmission occurred, and use other details from the admission as features that help the model make its prediction. When defining a prediction problem, you must clearly separate the target from the features. The target is the outcome you want to predict, which is unknown at prediction time but can be observed later. Features are the pieces of information available at or before the moment you make the prediction. For example, in an online store, if you want to predict whether a visitor will make a purchase, the target is whether they place an order, and the features could be pages viewed, time spent, device type, and cart activity. Aligning your data columns with this prediction question helps you label which column is the target and which columns are features. A single dataset can often be used to answer different prediction questions depending on which column you choose as the target. For example, with university data that includes demographics, grades, and graduation outcomes, you might predict whether a student will graduate in 6 years, using graduation as the target and earlier information as features. Or you might instead predict first-year GPA, making GPA the target and leaving out graduation status as a feature. The key step is to clearly define your prediction question and then align it with the appropriate columns so you correctly identify targets and features for your model. Classification and regression. When choosing a prediction target, first decide whether you are predicting a category or a number. If the target describes a group or label, such as yes or no for patient readmission, or spam versus not spam for emails, you are doing classification. In classification, the target consists of distinct labels like approved or denied. Recognizing that the target is categorical confirms it is a classification task and helps you focus on features that best distinguish between these categories. When the value you want to predict is numeric, you are doing regression. Instead of predicting a category or type, you estimate quantities such as how much, how many, or how long, like house prices, electricity demand, or travel time. In a dataset, these targets appear as continuous numbers, such as income or temperature. Recognizing that the target is numeric tells you that regression methods are appropriate and affects how you measure performance and interpret errors, which differ from mistakes in classification tasks. To set up a prediction task correctly, you must first decide whether it is a classification or regression problem. The same real-world situation can be framed either way, such as a bank predicting whether a customer will default or estimating how much money might be lost, or a streaming service labeling users as likely to cancel, or predicting the exact time until they leave. focus on whether your target outcome is categorical, like yes or no, or numeric, like an amount or a time. This choice guides how you define the prediction task, select features from your other data columns, and ensure the model supports your decision-making needs. Prediction timeframe. When you choose a prediction target, you decide both what outcome to predict and over what time period. The time frame is the gap between when you observe the input features and when the outcome occurs. For example, a hospital might predict whether a patient will be readmitted within 30 days or within a year, and even though the outcome is still readmission, the meaning and data labeling change with the time frame. To understand any prediction task, pay close attention to timing phrases such as within the next week or by the end of the month, because they define the prediction window. The prediction time frame determines which features you are allowed to use, because they must be available at the moment you make the prediction, not come from future events. If you want to predict a purchase during a current visit, you can use information like pages viewed and time spent on the site. If you want to predict a purchase within the next 30 days, you instead rely on past behavior such as previous visits. When working with data tables, choose columns that contain information known at prediction time as features, and use later outcomes as the target you are trying to predict. Changing the prediction timeframe can turn one problem into several distinct tasks, each with its own target. For instance, a bank may separately predict whether a customer will miss a loan payment in the next month, in 6 months, or in 2 years. These are different targets, even though they all concern missed payments. In a data table, each time frame can be a separate yes or no column, such as missed payment in 30 days or missed payment in 2 years. Clearly linking each target to its time frame helps you distinguish the tasks and choose features that are relevant and timely for each prediction window. Evaluating feature usefulness. Comparing feature perspectives. In prediction tasks, the same data can look very different depending on who is using it. A domain expert, such as a doctor or loan officer, interprets information through the concepts of their field, while a data scientist focuses on measurable variables and statistical patterns. As a result, what is a rich narrative for the expert becomes a set of features for the scientist. Moving between these views means asking how well each feature represents the real-world situation and where it might distort it, such as turning a doctor's description of a patient as frail into specific measurements, like age or lab results. When building models, users and builders often value different things. Users want features that feel intuitive and ethically acceptable, while builders may prioritize whatever gives the highest accuracy, even if it relies on complex or sensitive data. For instance, in hiring, recruiters might focus on experience and certifications, whereas data scientists might see online behavior as more predictive. To balance these views, we must consider not only accuracy, but also fairness and transparency, recognizing that a feature that looks strong statistically may be inappropriate in real-world use. When choosing features for a model, you need to balance short-term convenience with long-term stability. In the short term, it can be tempting to use features that are easy to collect and strongly tied to the target, such as recent purchases for predicting customer churn. However, for long-term success, you should favor features that stay relevant and unbiased over time, like study habits for predicting student success. This helps your model remain accurate and useful as conditions change and across different contexts. Spotting useful features. When choosing features for prediction, focus on whether each one has a logical connection to the outcome. For example, viewing hours or support interactions can reasonably relate to subscription renewals, while something like app color themes likely does not. A feature does not need a proven causal link, but it should be plausible that changes in it are associated with changes in the target. By consistently questioning how each feature might relate to the outcome, you can separate merely available data from features that are truly useful for prediction. When choosing useful features for a model, focus on those that vary and show a clear relationship with the target outcome. A feature that stays almost the same for all cases, like study time when most students study similar hours, will not help predict performance. In contrast, something like attendance, which differs more and aligns with passing or failing, is more informative. The same idea applies to housing prices, where factors such as number of bedrooms or distance to transport matter more than irrelevant details like door color. In general, features that change in recognizable ways with the target are more valuable than those that do not. When choosing features for prediction, focus on how specific, stable, and timely they are. Specific features give concrete measurements rather than vague categories. Stability means the relationships you see now are likely to hold in the future. Timeliness means the data is available at the moment you need to make a prediction. By emphasizing these qualities, along with checking that features are plausible and show enough variation, you can select features that are truly useful for predictive models. Information-rich features. An information-rich feature is a variable that provides a strong, relevant signal about the outcome we want to predict. In a prediction task, some features are closely tied to the result, while others add little or no useful information. For instance, when predicting student exam performance, the number of practice quizzes completed is much more informative than something like backpack color, because quiz completion reflects engagement and tends to correlate with performance. Evaluating features means checking whether they contain concentrated, meaningful information about the target, rather than random or superficial details. When choosing features for a prediction task, focus on how much new information each one adds beyond what others already provide. Some features, like house size and number of bedrooms in a housing price model, can be highly related, so once you know one, the other may not help much. In contrast, a feature such as distance to public transit can offer a different kind of insight that is not captured by size alone. Aim for features that contribute complementary, non-overlapping information rather than repeating what is already known. The usefulness of a feature depends on how accurately and consistently it is measured and how directly it relates to the process that produces the outcome. For instance, actual logged study time is usually more reliable than self-reported hours, and real-time sensor readings like vibration and temperature are more informative for predicting equipment failure than simply knowing how long the equipment has been installed. When choosing features for prediction, prioritize those that are measured well and closely tied to the true causes of the target, and avoid features that are vague, noisy, or redundant. Python code, information-rich features. This script visually compares how useful different simple features are for a model. It highlights which feature carries the most information. To keep the comparison clear and easy to interpret, it uses a very small synthetic dataset. We begin by importing two key libraries needed for our work. We use NumPy to handle numerical calculations and manage arrays, and we use the pyplot module from Matplotlib to create visualizations. These imports prepare the environment for later steps where we will manipulate data and generate plots. We set a fixed random seed in the numerical library using the value 42, so that any random numbers generated are the same every time the code runs. This makes the script deterministic, meaning it will always produce identical results under the same conditions. Such reproducibility is important for debugging, verifying behavior, and confidently comparing results across different runs of the program. We begin by using a numerical computing library to create a small array that represents study hours as our main feature. This array includes values from 1 to 8, each standing for a possible number of hours a student might study. It serves as a simple data set that lets us later examine how different amounts of study time relate to exam scores. We are modeling exam scores that mostly depend on study hours. Each score starts from a base value of 50, then increases by 5 points for every hour studied. To make the data more realistic, we add small random adjustments to these scores. This creates an array of exam results that are largely driven by study time, but still show natural variation from other factors. We create an array called backpack color code that holds a sequence of numbers representing different backpack colors, such as 1, 2, 1, 3, 2, 1, 3, and 2. This array is used as a feature in our analysis of exam scores. However, these numbers are intentionally chosen so they do not have any meaningful relationship with the exam results. This setup helps demonstrate what an uninformative feature looks like, in contrast to features that actually help explain or predict exam performance. We use a correlation coefficient function from NumPy to measure the relationship between study hours and exam scores. This function returns a matrix of correlation values, and we focus on the value in the first row and second column. That single number is the correlation between the two datasets and tells us how strongly and in what direction study time and exam performance are linearly related. We use a numerical correlation function to measure how strongly backpack color codes are related to exam scores. This function returns a matrix of correlation values, and we focus on the entry in the first row and second column, which gives the correlation between these two specific variables. By examining this single value, we can see how much, if at all, the uninformative feature of backpack color is associated with exam performance. The code reports how strongly each of two features is related to exam scores. It first prints the correlation between study hours and exam scores, using a previously calculated value rounded to 3 decimal places. It then prints the correlation between backpack color and exam scores, also rounded for clarity. Comparing these two values shows which feature is more useful for predicting exam performance. We create a figure with 2 subplots to compare different features side by side. Using a plotting function, we specify 1 row and 2 columns so that 2 plots appear next to each other. We also set the overall figure size to 8 by 4 inches. This layout lets us place 2 scatter plots together, making it easier to visually compare how different features relate to exam scores. We use a scatter plot to show how exam scores relate to study hours. Study hours are placed on the horizontal axis and exam scores on the vertical axis, with each student represented as a blue point. The plot is titled Study Hours versus Exam Score, and the axes are labeled to indicate that study hours are the feature and exam score is the target. This visual setup helps us quickly assess how changes in study time might influence exam performance. We create a scatter plot on the second subplot to compare exam scores with backpack color codes and look for any possible relationship between them. Each point is shown in orange for clear visibility. The subplot is titled Backpack Color versus Exam Score to indicate what is being compared. The horizontal axis is labeled Backpack Color Feature, and the vertical axis is labeled Exam Score Target, making it easy to interpret how backpack color might relate to exam performance. The code first calls a layout adjustment function from matplotlib to automatically tidy the spacing between subplots so that labels and titles fit clearly. This makes the visual comparison easier to read. It then calls the display function to show the figure on the screen, allowing us to visually compare how study hours relate to exam scores and how backpack color relates to exam scores. This script compares how useful 2 features are for predicting exam scores: study hours and backpack color. It uses synthetic data where exam scores mainly depend on how long students study. the correlation between study hours and exam scores is strong, while the correlation with backpack color is weak. Scatter plots show a clear positive trend for study hours, but no pattern for backpack color. Together, these results illustrate why choosing meaningful, information-rich features is crucial in data analysis. In this lecture, you learn to define features and targets in the context of supervised learning, identify features and targets in simple problem descriptions and tables, and compare alternative feature choices for a basic prediction task. In the next module, Module 3, we will go over math essentials.
Thank you for your attention. See you all in the next lecture.